Welcome to part 2. What number are we on? 7. The polynomial function f is given by f of x equals x minus 4 times 3x minus 1, which of the following description of f is true. This tells us we have, this would tell us that x equals 1/3 is a 0, x equals 4 is a 0. This one has a multiplicity of 2. So we should have, okay, so let's see what the question is asking us. F is a polynomial of degree 2. Well, that's not true. It has to be at least I have a 1 here and 2 here, so it is at least a degree 3. 2 is also wrong. So degree 2. Polynomial is degree 3. That's right. Polynomial is degree 3. And its leading coefficient is either 9 or 3. To find the leading coefficient, normally we would have to FOIL this out. 3x minus 1. I'm going to write this twice just to show you guys what's going on here. So this is x minus 4 times 3x minus 1 times 3x minus 1, or 3x minus 1 squared. And so all we have to do is to find the leading term, all we have to do is multiply all these leading coefficients together of each binomial. So we have x times 3x times 3x, which should be 9x to the third. So we should have a leading coefficient of 9. D. Okay. Values of the polynomial function f for selected values of x are given to the table if all the zeros of the functions are f on the table, which must be true. All the zeros are given. So this is one we did in class, but just to reiterate, I have a bunch of points here, so like a -1, -36, 1 zeros, throw that right there, 3, 4 is over here, say 5 zeros there, and then 7, 12 is over here. And we should know, do any of these have to be true? So the function has to have a local minimum at -1, -36. And it doesn't. Like if I draw this right here, and then I connect all these dots, it would not be that case there. So I'm gonna just draw my little thing right here. There we go. So that would prove that -1, -36 does not have to be a minimum because I just sketched it that way, and I still have only two zeros, and I've gone through all the dots. Function f has a local minimum at 5, 0. So I have 5, 0 here. This one I think has to be true. If I dip down lower, I have to come back up and touch that x-axis again. So I think that one is right, because if 5, 0, if I can't, let's see what the other ones do. 3, 4 has to be a local maximum. Well, I have it sketched already, and 3, 4 is not a local maximum on here, so that one doesn't have to be true. It could be, but it doesn't have to be. Oh, get it back in frame. And then there has to be a local max at 1, 0. This is 1, 0, and this is not a local max, so that one doesn't have to be true. So it is B. Okay, this guy right here. The graph of the polynomial function g is given. The function f is defined for 0 is less than x, less than 3, and is identical to the function g on that interval. How many total local minimum and maximum does the function f have? So the biggest issue with this one has been people look at this graph and assume it is f. It is not. This is the graph of g, and it describes what f is. F is only from 0 to 3. Only from 0 to 3. And my wife is coming in here. Say hello to everybody. Hi. Thank you. Brought me a drink. So nice of her. So nice. Okay, so it's between these two spots and it's identical, so it's going to look exactly like this. that is function f. And what are all of its local minimums and maximums? So I have a 1 here, and then these here on the edges also count, so the answer should be 4. 4 local mins and maxes. Let's go for the next page here. 12. The graph of the function f is given for -3 all the way to 6. So from -3 to 6, so that is the entire graph, that interval. Which of the following statements about the rate of change of f over the interval 2 to 6? So the rate of change, the interval from 2 to 6. So about from there to there. We need to figure out what's true about this rate of change. So the rate of change is positive. That means the graph is going up. So if the rate of change is positive, this means that f is increasing, or f is going up. But that is not the case because f is going down here. So it describes the first part, but not the second part. The rate of change is negative. That means f is going down. But it's going down the last half, but up on the first half, so that's not true. This says the rate of change is increasing. So increasing, that would mean that f is concave up. And so if I sketch a line right here, this is a tangent line, so sketch a tangent line, and it looks like the graph is below, on this point right here, the graph is below the tangent line, so that one can't be right either. And so the rate of change is decreasing. Well, the rate of change, that means concave down. And yes, this entire interval is going to be underneath the tangent line. It looks like it's concave down all the way. So that is the best answer. Okay, number 13. The table gives the characteristics of the rates of change of the function f at different intervals. So it's the rate of change. Which of the following is true about f on the interval 3, 4? So that's this interval right here. So if the rate of change is positive, that means it's going up, or f is going up, f is increasing. And if the rate of change is decreasing, this means that f is concave down. Concave down. Highly suggest you put this on your cheat sheet. Make sure you get the rate of change and how they translates to what's happening with f. So we want to find going up or increasing and concave down for f. So f is increasing. That's what we said, going up. So check. And the graph is concave down. So that is also true. F is increasing. Yes, it's concave up. Nope, that should be, so this is not true. Just check them all to be sure. F is decreasing. No. F is decreasing. No. So therefore it must be A. Must be A. Okay. We're not doing 14. Let's go ahead and I'm going to pause this video here and we'll see you in part 3.